All right, good morning. Welcome back to Math 104. We're going to continue with our discussion on Unit 4. So last class we talked about completing the square, how we had to essentially move the constant term over, and then we had to take half the b term and square it, that quantity you add to both sides. And then we would rewrite the left-hand side, our trinomial, as the square of a binomial. Obviously combine the constants on the right-hand side and then use the square root property. So for today's class, we're actually going to learn how to use a quadratic formula. This is actually really nice. It's definitely something you've probably seen in the past. And it is a way for you to solve quadratic equations every single time because it will always work. Let's take a look at our notes and we'll talk about the 3 ways for solving so that we understand the differences. And then we'll look at quadratic formulas. So there are 3 ways for solving a quadratic equation like x squared plus 5x minus 14 equals 0. We could attempt to factor, but unfortunately that doesn't always work. We could complete the square, which definitely always works, and we could use a quadratic formula. So what I wanted to show you right now is how we would apply the quadratic formula. What I'm going to write down here for you is the formula x is equal to, this is a quadratic formula, so let's go here, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That's essentially the entire quadratic formula. Be very careful. You want both terms in your numerator. Here's your first term, here's your second term. You want both of them to be over 2a. Okay, now in terms of how we do this, what we could essentially do initially is we could start by dividing out my leading coefficient. We actually don't have to do this, but I want to demonstrate how this is similar to what we've done before. We could say A is 5, B is 15, C is negative 40. Or we could recognize that 5 is a common factor, so why not divide every term by the leading coefficient? So we're going to divide every term by the leading coefficient. What I'm going to do is I'm going to do the same thing on the right-hand side. So our focus is to get our leading coefficient to be a 1x squared, a 1, right? The leading coefficient. So here's what we end up with. We have x squared plus 3x minus 8 is equal to 0. So there's our first expression. Then on the right-hand side, notice the a's are going to cancel. So we're left with x squared plus b over ax plus c over a is equal to 0. Hopefully so far so good. Now, what we're going to want to do here is, you know what's interesting is, we could essentially use completing the square to derive that quadratic formula, which might actually be pretty interesting to kind of see. So I'm actually going to do that with you right now. So what if I added a to both sides and I start by going through the process of completing the square, something that I'm used to, right? And again, I'm going to do the same thing on the right-hand side. Let's subtract this c over a. I'm going to take a different approach here. So we have x squared plus b over ax is equal to negative c over a. When we complete the square, remember we always take half of the b term and then we square it. So essentially we want to write this as a perfect square. So we're going to do half of the b term. So half of 3, which is 3 halves. And that's what goes in my parentheses. And then we square it. So 3 over 2 times 3 over 2 is 9 over 4. What you do to one side, do to the other. Notice that I've added the 9/4 to both sides. When we combine 8 plus 9/4, that's going to give us 41/4. You can do the math to verify that that is actually correct. Let's follow the same procedure on the right-hand side. We are going to write out a space for us to write the square of a binomial. We know that x is our leading term. We're going to take half of our b term. So essentially, when you think of half of b over a, think half of means times. So 1/2 times b over a is b over 2a. Now you're going to square this. So you take half first, then you square. B over 2, oh, hi, Kim. I'm just going to spotlight my video. Good morning. I'm so glad you can join us. So we've got b over 2a, and we're going to square this quantity, and that leaves us with plus b squared over 4a squared. Now what you add to one side, you must add to the other. So b squared over 4a squared. When we combine these two, so b squared over 4a squared plus a negative c over a, or however you would like to look at that, you actually end up with b squared minus 4ac all over 4a squared. Remember, think about how you add or subtract fractions and the fact that you need a common denominator. So I'll let you again play around with this so that you can verify each of these pieces. Now, since I have x plus 3 over 2 squared, and that's equal to 41 over 4, I'm now ready to take the square root of both sides. So let's go ahead and take the square root of the left and take the square root of the right. Notice those cancel, leaves us with x plus 3 over 2 is equal to positive or negative square root of 41 over 4. We're going to do the same exact thing on the right. So let me rewrite it because it's a little messy. So we have x plus b over 2a squared is equal to b squared minus 4ac all over 4a squared. So let's take the square root again, both sides. Notice the square root and the square cancel out, just like we saw over here. And we have x plus b over 2a is equal to the square root, positive or negative, b squared minus 4ac all over 4a squared. So far, so good. Notice on the left-hand side, we have square root of 41 over square root of 4. We know that square root of 4 is a perfect square. So square root of 4 is just 2. So I can say, well, this is x plus 3 over 2 is equal to positive or negative square root of 41 over 2. That's the first thing we can consider, which is actually pretty nice. The next thing we have to do is subtract the 3/2 to bring it over. So that means my final result will be negative 3 over 2 plus or minus square root of 41 over 2, which is the same as a negative 3 plus or minus square root of 41 all over 2. That's essentially the exact same thing. And if you'd like, I can actually write that down. X is equal to negative 3 plus or minus square root of 41 all over 2. So these are the same expression, just written slightly differently, of course. Now notice over here in our denominator, we also have a perfect square. This is actually really interesting, and we're almost done deriving the quadratic formula. The square root of 4a squared is 2a, right? Because those are both perfect squares. Check this out. So x plus b over 2a is equal to positive or negative square root of b squared minus 4ac all over 2a. Subtract b over 2a from both sides. And now we've derived the quadratic formula. X equals a negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a, which is the same as negative b plus or minus square root of b squared minus 4ac all over 2a. And there you have it. Okay, so by using the completing the square process, which is something we were already familiar with, we can actually derive the quadratic formula. Okay, very cool. Use a quadratic formula to solve equations. So like I said before, any quadratic equation can be solved by the quadratic formula. Now there's a couple things we want to be careful when we actually solve So for instance, notice here that let's say we had x is equal to 2 plus or minus 4 all over 2. Just by canceling out the 2's and that's it, and saying, oh, your answer is positive or negative 4, that's hugely, hugely, hugely incorrect. Recall, and I'm sure you won't make this mistake, but recall that this is the same as 2 plus 4 over 2 and 2 minus 4 over 2. We have to split up those solutions and then look at them each at a time, basically. So this gives us 6 over 2, but 6 divided by 2 is 3. So my first solution would be a 3. And then 2 minus 4, which is negative 2 over 2, becomes negative 1. So here are my two solutions. We're allowed to do this. We break it up into two separate fractions and then we simplify. We are not allowed to cancel terms. We've already learned that. Notice here we canceled out our coefficient of our second term, which is a huge problem because you're literally ignoring the fact that that 4 is also over a 2. So what may help in this case, and here's another way to look at this, you could write 4 over 2 plus or minus 2 squared to 5 over 2. We can simplify this by rewriting as two fractions connected by that plus minus. Instead of writing 4 over 2 plus 2 squared to 5 over 2, and then 4 over 2 minus 2 squared to 5 over 2. We can split the two fractions, and then I can notice here that, oh, wait a second, 4 divided by 2 is 2. And now I can simplify those, and that leaves me with the square root of 5. So we can reduce here and reduce here. That leaves us with 2, okay? We're allowed to do that. We're allowed to reduce fractions themselves. But what you're not allowed to do is cancel out parts of terms just like this. It's not, you cannot do that. Last one, this is a huge mistake. Notice that we're showing here that we're canceling the denominator with the radicand. Like what? That doesn't even make any sense at all. What we would want to do in this case is split the fractions up. So 4 over 2 plus or minus 6 squared to 2 over 2. And then obviously we reduce just these pieces, just our numeric pieces, which are in front of that radicand. So 4 over 2 is 2. And 6 over 2 is 3, but we're still left with the square root of 2. Something to think about as you find your answers. Okay, so we want to solve each of these by using the quadratic formula. What's really nice about this is that we don't really have to do much to it. My only suggestion is, and actually what you kind of have to do, is you want to make sure that your equations are in standard form. As a reminder, standard form is when your equation is equal to 0. You've done this 1,000,001 times. Every time we go to solve a polynomial of degree 2 or more, you say set it equal to 0. And then typically you would say, let's try to factor. In this case, we're not going to worry about try to factor. We're just going to use a quadratic formula. My advice for part A is to bring the 25x squared over. So you have 0 is equal to 25x squared plus 10x plus 1. That's my advice. Bring the leading term, bring the term with the highest degree over to all the other terms. Since it's negative, that makes it a positive term, and it's much more manageable. Not that it matters, honestly. You could have brought the 10x over and the 1. It's just less work, right? At this point, we're ready to identify what are my A, B, and C values, right? So think of this as 0 is equal to ax squared plus bx plus c. We've done this before identifying ABC, especially when we were using AC grouping and trial and error. So we notice here that A is 25. Don't include the variable, but you already know this, so I'm not worried. B is equal to 10, and then C is equal to 1. All we have to do now is just plug this into the quadratic formula. Can I please urge you to write down x equals and then the quadratic formula? It is not enough just to write the quadratic formula. You must have x equals this value. What you're basically doing here is you're finding the x-intercepts. That's what you're finding. You're finding the zeros where the graph crosses through the x-axis. That's essentially what you're doing. So you must have your answer as x equals and then what those zeros or those x-intercepts happen to be. Okay. Let's use the formula. So x is equal to negative b, so negative 10, plus or minus the square root of b squared, so 10 squared, minus 4 times a times c, all over 2a. So 2 times 25. Perfect. So now we want to evaluate each of these pieces. Welcome, James. Now we want to evaluate each of these pieces. So we've got x is equal to negative 10 plus or minus. What I would do if I were you is I would just simplify everything underneath. Like I would say to myself, well, I know that we've got 10 squared, and 10 squared is 100, but we could just write 10 squared, then minus 4 times 25 times 1. Not that we need to write times 1, but it's okay. So it turns out that 10 squared, which is 100, minus 4 times 25, which is also 100, leaves us with a 0. And that's not a big deal. Don't freak out about that. 2 times 25, that's 50. Now, interestingly enough, we know that the square root of 0 is 0. So what ends up happening is that our solution is essentially negative 10 plus or minus 0 over 50, which really just means my solution is x is equal to negative 10 over 50, which reduces to negative 1 over 5. All this means is that for my particular parabola, I have a double root. And we don't really have to focus on this too much, but I actually think it might be helpful for you to see this particular graph like actually shown. So what I'm doing right now is I'm taking a second to write or type this particular equation into Wolfram Alpha so that I can show you what this looks like. So let me share my screen with you. All right, thanks, James. That's awesome. Let me share my screen with you. Okay, so check this out. Here's a graph of 25x squared plus 10x plus 1. It is a parabola. And notice that it only hits the x-axis once. And it literally hits at exactly negative 1/5, comma 0. So if we kind of take a look, notice it provides a solution too, which is awesome. We can verify that we did this correct. I love Wolfram Alpha for that because it's very robust. You can do so many different things in Wolfram Alpha. And one of those is to visualize what your graphs look like. So you can, get an idea of what's happening here. So it's hitting the x-axis at negative 1/5, and then it's going right back up. That's essentially what's happening. I want you to notice too, that if I put this line that I've got, this vertical line through my red dot at the bottom, doesn't it look like it's symmetric on either side of that line? That's kind of a very interesting feature about parabolas. It seems like you are equidistant on either side of that line of symmetry. So if I move this down, do you see how it's exactly the same on either side? That's kind of neat. And again, I'm trying to stay as center as possible. That's one of the properties of parabolas. So for instance, your x squareds, your equations of degree 2, that's a property of those types of equations, that it gives you a parabola that's symmetric about the axis of symmetry, about the line in the center. So that's actually something you should think about. Okay, perfect. Let's go ahead and check out part B. Same thing, we're going to identify what's my A, what's my B, what's my C. A in this case is 1. Remember, it's our leading coefficient. A is 1. Notice here B is a negative 1/2. And you're probably thinking, oh, fractions again. And it really isn't a big deal, I promise. And then C is a negative 3/5. For some of these, it just might take a little extra time, but I don't want you to shy away from it. Okay, so we have x is equal to negative b. So notice we have a negative b, but my b is a negative 1/2. When you think about this, I want you to say negative 1/2 because it's a negative b. So negative 1/2, and actually I'm just going to write it out because I don't want you to be wondering where I put that negative or what happened. So I'm actually just going to write it out. I'll simplify it in a second. plus or minus square root of b squared, so that's a -1/2 squared, minus 4 times a times c, all over 2a. Okay, that ended up being not too bad. Now all we have to do is just evaluate. So -1/2, that's a +1/2. Plus or minus square root of -1/2 squared, that's the same as -1/2 times -1/2, which is +1/4. When we have -4 times 1 times a -3/5, imagine this 4 over a 1. Don't overthink it. It's just -4 over 1 times -3/5. That's going to give you +12 over 5. And all of this over 2. You're going to want to do some side work, of course, to combine your essentially your 1/4 and 12/5. So we can definitely do that. So we have, or you can just use your calculator. So 1/4 plus 12/5. And that's going to give us, let's change it back. That's going to give us 53 over 20. So we have x is equal to 1/2 plus or minus square root of 53 over 20 all over 2. So we're finding that this is kind of starting to be a pain in the butt. What we'll end up having to do is rationalize this. But what I would suggest to you is that it is very possible that when we are solving an equation using the quadratic formula, it's very, very possible that the software that you're using may ask you to provide your solutions in decimal form. So instead of going through the process of rationalizing and blah, 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 and subtracting and dividing by 2, what I'm actually going to suggest to you is let's actually plug this in and find decimal solutions, okay? So 1/2 is simply 0.5 plus or minus. So then we have this square root of 53 divided by 20, okay, which gives us 1.62788, and then all over 2. So I would split this up. I would start with adding the numerators, then divide by 2, and then I would subtract the numerators and divide by 2, like so. We are going to do 0.5 plus 1.62788, and then let's divide by 2. So one of my first solutions is 1.06. We'll round to the nearest hundredths. We're going to do the same thing. So 0.5 minus 1.62788. And then we'll divide by 2. And we'll find that our next solution is -0.56. So here are my solutions to this problem. If you're wondering when we can do this, just look at Lumen and determine if it's asking, does it want a decimal? You know, it would say round to the nearest tens or hundreds place, or does it want an exact value? I will tell you that typically you won't see problems like this in your Lumen. Another way to do this, to correct it, is the following. Let me teach you really quickly. It's a very small fix. So we started with an equation that had a bunch of fractions, right? Which is highly annoying. Why not multiply by the LCD to cancel fractions? That's going to be really helpful. So let's multiply every term by 10, since that's my LCD. That gives me 10m squared minus 5m, right? Because 2 goes into 10 5 times. 5 goes into 10 twice, so 2 times 3 is 6. N is equal to 0. Once you have this so that you have no fractions in your equation, we can say A is 10, B is -5, C is -6, and then we go through the process and we can find an exact value. So a couple things to think about if you ever wanted to ensure that you can find an exact value If you have an equation with fractions, let's just cancel them out. Cancel them out and then go forward from there. Very nice. Let's turn the page. Okay, take a look at example 15. Given f of x is equal to 3x squared plus 6x, find all values of x for which f of x is equal to -9. What this is telling us is that f of x in our equation is -9. So it's asking us to sub out f of x with -9 and then find the values of x for that make that true. So I'm going to replace f of x with -9. And we have -9 is equal to 3x squared plus 6x. This is very different from evaluating f at a given value. If this said f of -9, like f and then -9 here, then we'd replace each x with a -9. That's not what we're doing. All we're doing in this case is actually subbing out f of x with the -9. Okay, we are going to use a quadratic formula, but we want to write this equation in standard form first. That means set it equal to 0. So we have 0 is equal to 3x squared plus 6x plus 9. I do want to point out to you that if you can ever save yourself a little bit of time and headache, you should. So for instance, with this particular problem, do you see that there's a common factor of 3? Do you see that I could divide every term by 3 evenly so that I can essentially bring this equation to simpler terms? And I think it's worth doing. You don't have to, you'll get the same answer even if you don't do this, but it's worth doing. So let's divide every term by 3. That means we're left with 0 is equal to x squared plus 2x plus 3. Perfect. Now, of course, we can attempt to factor this, but I actually want us to use a quadratic formula. And just to verify something, there are no factors of 3 that combine to give you 2. So even if we wanted to factor it, immediately we'd see that we hit a roadblock because you cannot find factors of 3 that add up to 2. Okay, your signs are the same, they're both positive, so it's not going to work. All right, let's write out each of our coefficients. So a is equal to 1, b is equal to 2, c is equal to 3. Let's use the quadratic formula. X is equal to -b plus or minus square root of b squared. B squared, 2 squared is just 4. I hope you're okay with me just, jumping into that. Minus 4 times a times c. All over 2a. All right, let's simplify what's under the radical. So we have x is equal to -2 plus or minus square root of. Now we have 4 minus 4 times 3. Well, 4 times 3 is 12. So we have 4 minus 12, which is going to give us -8. All over 2. Notice what's happening here. The square root of -8. Let's do a little bit of side work to see what's going on. As soon as we see the square root of a negative number, we remember that this is essentially imaginary. So we're going to take out I from under the radical. So essentially we're taking out the square root of -1 and we're rewriting it as I. So we have I square root of 8. When we see square root of 8, we say, well, let's break it down. We're going to break this down into the perfect square and its other factor. So square root of 4 times 2 is the same as square root of 8. Square root of 4 is our perfect square. So this becomes 2i square roots of 2. Okay, beautiful. Let's go ahead and replace square root of -8 with 2i square roots of 2. X equals -2 plus or minus 2i square roots of 2 all over 2. I'm betting you're going to see what happens. You're probably noticing that we have a lot of 2's, and in which case we're going to divide 2 out of each term. Yes, as long as you said divide 2 out of each term, then I will agree with you. Another way we can do this is rewrite it first so that we can see it clearly. -2 over 2 plus or minus 2i squared of 2 over 2. So both terms are being divided by that 2. Now let's just simplify. Negative 2 divided by 2 is a negative 1. Plus or minus, notice the 2's are going to cancel. And that leaves us with I squared of 2. So my two solutions are negative 1 plus I squared of 2 and negative 1 minus I squared of 2. Okay, this is something that you'll definitely see. This is on par with problems that you will see again and again and again. Awesome. What I've done here is provided you with a summary of all the things that we've learned so far in this unit. So essentially, notice with step 1, if the coefficient of x squared is a negative, divide everything by negative 1. If a, b, and c have a GCF, you should divide that. You should divide it out. So you're reducing that equation. So it has smaller coefficients, which makes it a lot easier to deal with. And then notice that I've provided to you the different methods. So factoring and using the zero factor property. This has limitations because it has to be factorable. If it's not, you can't do this. But if you can, you'd set it equal to 0 and then you'd factor and then set each factor equal to 0 and you solve, right? If you could use the square root property, then your equation has other limitations. It's got to be a constant and a squared term. That's it. So for instance, it would look something like this, where you have a squared term and a constant. Then you just take the square root of both sides, and obviously you don't forget the plus or minus. Your other method is completing the square and then using the square root property. So this actually always works. It's really even easy to use even when b over a is an even number, right? So even when it's an odd number, even when b is odd and you're cutting it in half, it's really not even a big deal. So this is pretty straightforward to use, even if you have fractions. And then lastly, the quadratic formula. Again, it always works, right? Identify your a, your b, your c, plug it in, and then solve. The point of all of these is that, for instance, with this one, standard form, our first one, standard form. So just be really, really careful. Completing the square has its own set of steps where we recall that we divide the term, the leading term, by that coefficient, divide everyone by that value, and then make sure you bring the constant over. So it would look like, you know, your squared term, your linear term. We usually leave like a gap here, and then it'd be equal to the constant. And you essentially go forward from there, okay? And then, of course, use a square root property. Practice all of these techniques. You've done this a million times. Practice these 3 techniques for sure. And identify when you should be using those. Perfect. What we're going to learn now is about something called the discriminant. The discriminant helps us to determine the number of real solutions or imaginary solutions. It doesn't tell us what they are. It just tells us, are we going to have real solutions? Is it 2 of them? Is it 1 of them? Or are we going to have imaginary solutions, right? So how we figure this out is we simply look at the discriminant. Now, in our quadratic formula, x is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. The discriminant is just the radicand of my formula. So the discriminant is just my b squared minus 4ac, that part. Now, depending on the value of that part, this sign will tell us how many points are on the x-axis. It'll tell us, do we have 2 solutions? Do we have 1 real solution? Or do we have none? So for instance, let's take a look at the following chart. So it says solutions of a quadratic equation essentially based on the discriminant. What can we expect? If the value of the discriminant, the b squared minus 4ac, if that's positive, meaning it's greater than 0, what that implies is we're going to have 2 real solutions. That's exactly what that means. If it's positive, so for instance, you know, I'll give you an example. x is equal to, let's do 1 plus or minus 2 squared to 3 all over 5, right? As an example. What this says is that when we go ahead and we graph this, because I know that my 3 is positive, I'm going to end up having 2 real solutions. So it could look something like this, where I cross the x-axis at 2 locations. That's essentially what we're saying. If that discriminant is positive, we know we're going to have 2 real solutions. We just don't know where they are. If the discriminant is equal to 0, what this implies is that we have only 1 real solution. We saw this already in our previous example. We found that we had x was equal to -1/5, right? That was the only solution we had. And then when we graphed this, we noticed that it looked something like this, where it crossed the x-axis at only 1 place, which is fine. It's not a big deal. We knew this because essentially the numerator is plus or minus square root of 0. So my discriminant, since it was a 0, told me, oh, this plus or minus square root of 0, this essentially goes away because it's just 0. And it leaves me with 1 solution. So it hits the x-axis at that point and bounces right back up. This can be the case if we had a negative x squared. So it could essentially be a concave down parabola. So it could hit the x and then continue by bouncing back down. So the parabola, that U shape, it can be open upwards or it can be open downwards. It depends. And then if the value of the discriminant is negative, so for instance, we have, let's write x is equal to 2 plus or minus square root of -4. Notice that my discriminant is negative. What that should tell you immediately is that we have an imaginary solution. So what this tells us is that we have 0 real solutions. So 0 real solutions. And essentially what this means is we have 2 imaginary solutions. That's what that means. In essence, what this is also saying to us is that when we look at a graph that has imaginary solutions, that parabola never actually crosses the x-axis. It's floating somewhere either above it or below it, which is actually quite interesting. So depending on that discriminant, we'll be able to say, is this graph going to cross the x-axis? Is it going to cross twice? Is it going to hit the x-axis at 1 point? Or is it just going to hover either above or below it and never actually physically cross the x-axis? That's what the discriminant will tell you. Let me show you. Without actually finding the solutions, let's use a discriminant. Let's see if we have 2 distinct real solutions, a single real solution, or no real solution. First things first, A is equal to 4, B is equal to -12, C is equal to 9. We identify our A, our B, and our C. I'm going to use B squared minus 4AC. So let me write out B squared minus 4AC because we're determining what's happening here. B is -12. So make sure you write in parentheses. You don't want to forget that you're squaring that term. -4 times A times C. Let's go ahead and plug this into our calculators. So we have -12 squared. Use the parentheses, otherwise it's not going to understand what you mean. It's going to think you're squaring just the 12 and not the negative. -4 times 4 times 9. So I'm literally writing down exactly what I have here. I get 0. So because this is equal to 0, my discriminant is equal to 0, we realize that we have 1 real solution. It's going to hit the x-axis and bounce right back. If we go into Wolfram Alpha and we type in 4x squared minus 12x, and I'm going to show you this in a second, plus 9, I have the following graph. Let me share with you what I'm looking at. Notice it hits at exactly one solution. It hits the x-axis once and bounces right back up. Okay, let's take a look at the second example. We have to set this equal to 0, so let's bring the 2x over and the 8. So in order to bring the 2x over, I have to subtract it. And in order to bring the 8 over, I have to add it. Now that I have my, let's separate this, it's a little too cramped. Now that I have my equation in standard form, I'm going to say A is equal to 3, B is equal to -2, and C is equal to 8. Let's plug it into b squared minus 4ac. B squared minus 4ac. B is -2. Minus 4 times a is 3 and c is 8. Same thing, we can go through the process of punching this into our calculator. -2 squared minus 4 times 3 times 8. And that's going to give me -92. So this is equal to -92 in this case. Because my b squared minus 4ac is negative, what that means is that there are 0 real solutions. I don't know what they are. I just know that this has 0 real solutions. What that implies is that if we were to look at this graph, it would not actually cross the x-axis. I like plugging these in so that you can see what this is looking like. It's going to be really helpful to you too if you wanted to check this out visually and just kind of supplement your learning. So I'm going to share with you the Wolfram Alpha. Let's take a look at this graph. And there it is. Notice your x-axis is all the way down here. It's hovering above it. It's never going to actually cross the x-axis because its solutions are not real. Okay, notice it has complex solutions. It even tells us what those are. Very cool. Last one, you could probably guess what this is going to be, but whatever. So always write this in descending order. This is like a problem is trying to trick us. 3x plus 2x squared is equal to 4. That 2x squared is going to come first, then the 3x, and then of course bring the 4 over. We do that by subtracting 4. Once I have my equation in standard form, we'll write down that a is 2, b is 3, and c is -4. So we'll take b squared minus 4ac. Let's plug these in. 3 squared minus 4 times 2 times -4. Take a moment again, plug this into your calculators if you want, or just do this, by hand. It's completely up to you. It doesn't matter. When we do this, we get a 41, a positive 41. Because my discriminant is positive, that tells me I have 2 real solutions. So when I graph this, it's definitely going to cross the x-axis in 2 locations. So we have 2x squared plus 3x minus 4. Let me share with you the graph so that you can see how it crosses the x-axis in 2 locations. Let's share Wolfram Alpha one more time. And here you have it. Okay. The discriminant, again, as a reminder, does not tell us what the solutions are. It just lets us know whether or not it actually crosses through the x-axis. In this case, it crosses through 2 places, which means it has 2 real solutions. Very nice. Let's go ahead and turn the page. Okay. For this section, we want to determine a quadratic equation given its solutions. This is actually quite an interesting piece here. So let's start by reviewing solving by factoring, right? Let's start by looking at what happens when we can actually factor and solve. So we want factors of -6 that combine to give us a +1. Well, that's got to be +3 times -2. So let's factor using trial and error. So x plus 3 times x minus 2 is equal to 0. Well, when we saw something like this, you would set each factor containing a variable equal to 0, right? And then you would say, let's solve them. You would start by subtracting the 3 on this side and say, oh yeah, I see that x is equal to -3. And then on the other side, you would obviously add 2 and say, okay, x is equal to +2. Now, what we want to do instead is we actually want to go backwards. So what if instead I told you what the solutions are? And I said, hey, what was the original polynomial? We can easily do this. If I know that my solutions are -3 and +2, if I wanted to go backwards to find the original polynomial, you essentially want to take your steps backwards. So what was it before x was equal to -3? Well, that's easy. It was x plus 3 is equal to 0. And it was x minus 2 equals 0, right? That's essentially what it was. And the only reason you set them equal to 0 is because they were part of the polynomial in factored form. So we'd write it out like, oh, okay, this actually means x plus 3 times x minus 2 is equal to 0. And then you'd go ahead and you'd distribute and you'd find that it was x squared minus 2x plus 3x is plus 1x, and then minus 6 is equal to 0. And you just determined the original polynomial equation. So that's essentially what we're going to be doing right now. We want to find the original polynomial given the solutions. Okay, perfect. How to derive a quadratic equation when given the solution. Step number 1, write each solution A as an equation. So notice for part A, that's provided to us. X is equal to 1, x is equal to -3. Number 2 says clear fractions as needed. This is after you write the equation. So this is something to think about. You can clear fractions as needed. So essentially you can write each solution as a linear factor set equal to 0. Then you essentially construct a product of those factors and you multiply them together. That's what's going to give you your original polynomial. Okay, let's check it out. This first one, we're going to subtract a 1 so that we have x minus 1 is equal to 0. For my second equation, I'm going to add 3, and that gives me x plus 3 is equal to 0. Notice our two factors are x minus 1 and x plus 3. This is why we set them equal to 0. So let's go ahead and write them together so that we can actually multiply them. X minus 1, x plus 3. Let's go ahead and distribute. So x squared plus 3x minus 1x is plus 2x, and -1 times 3 is minus 3. So our original polynomial in this case is x squared plus 2x minus 3 is equal to 0. I want to point out that this equation has two real roots. There are 1 and a -3. Those are real roots, right? There's no imaginary piece to this. So what this is telling us is that the original corresponding function was y is equal to x squared plus 2x minus 3, which has two x-intercepts, right? Which is why we were able to say, okay, here are my solutions. Let's find the original polynomial. All right, let's take a look at part B. For part B, we have fractions, so we may want to start by clearing them. What I'll do is for this first equation, I'm going to multiply both sides by 2. That gives me 2x is equal to 1. We're going to subtract the 1, and we have 2x minus 1 is equal to 0. So our first factor is 2x minus 1. For this second equation, let's multiply by 4. That gives me 4x is equal to 3. Subtract the 3, and we have 4x minus 3 is equal to 0. Here's my second factor. So let's go ahead and write 2x minus 1 times 4x minus 3 is equal to 0. Now that I have my product written down, let's actually distribute and see what we get. 2x times 4x is 8x squared. 2x times a -3 is a -6x. I might as well write it out. Negative 1 times 4x is negative 4x. And then negative 1 times negative 3 is positive 3. Combine like terms. You have 8x squared, negative 6x, and another negative 4x is negative 10x, plus 3 is equal to 0. And there is your original polynomial. So if I give you solutions, you can easily tell me what the original polynomial was. Notice again, in this case, we do have two real solutions, a 1/2 and a 3/4. Even though they're fractions, doesn't mean they're not real. Okay? Let's try one that's a little bit more complicated. Take a look at part C. Notice here that I have two imaginary solutions, 2 plus I, 2 minus I. The idea behind this stays exactly the same. We have to set each of these equal to 0, right? We want to figure out what it was before we solved. So here's how we do it. We essentially subtract the 2 and subtract the I. So if I subtract the 2 and subtract the I, my first equation is x minus 2 minus I is equal to 0. I'm going to do the same thing with my second equation. I'm going to subtract the 2 and add the I because it's a negative, right? So we want to use the opposite operation. So I have x is equal to negative 2. Wow, let me try. Hold on, I'm writing things weird. Gotta love it. X minus 2 plus I is equal to 0. There we go. X minus 2 plus I is equal to 0. Now, let's go ahead and write this out. X minus 2 minus I as a product of my factors. X minus 2 plus I is equal to 0. I do not want you to panic when you see something like this. I want you to realize that this represents a trinomial times another trinomial. Recall that when you have 3 terms times 3 terms, that's going to give you 9 terms when you distribute. So don't freak out. It's really not bad. You just have to distribute, right? Let me show you. We're going to start with x and we distribute. X times x is x squared. X times negative 2 is negative 2x. X times positive I is positive ix. Once we're done with our first term, our x, then we move to our next term, which is the negative 2. So we go negative 2, negative 2, negative 2. We just distribute each to each term in the second set. Don't overthink it, right? Negative 2 times x is negative 2x. Negative 2 times a negative 2 is positive 4. Negative 2 times positive I is negative 2i. We still have one more term in the first set of parentheses, so we take that term and we distribute to everything in the second set. So I have negative I times x, which is negative ix. Negative I times a negative 2, which is positive 2i. And negative I times positive I, which is negative I squared. Good. As a reminder, whenever we see an I squared, we know that that is the same as negative 1. All right, let's clean this up. There's a lot going on here. Okay, first things first, I have an x squared. I don't see any other x squared terms, so I'm just going to write that down. Next, I have a negative 2x, another negative 2x, and that's about it. So negative 2x and negative 2x is negative 4x. Next, I have plus ix and minus ix. Well, that's cool. So these are opposites. They cancel each other out. We already used these two. We have a positive 4, right? Notice we have a minus I squared. So if you wanted to, you can write plus 4 here. Notice we have a negative 2i and a positive 2i. So these are opposites. They also cancel each other out. And then you have minus I squared, but I squared is -1. So it's a minus a -1. So now we just want to finish this up by combining like terms. -1 is a +1. So when we rewrite this, we should note that our original polynomial is x squared minus 4x plus 5 is equal to 0 because it's 4 plus 1. And that is how you proceed through this problem, even though we had imaginary roots. The corresponding function to this problem is y is equal to x squared minus 4x plus 5. And again, it has 0 x-intercepts because it doesn't cross the x-axis. It has 2 imaginary roots. Okay. Hopefully that made a heck of a lot of sense. At this point, I do want to just take a 5-minute break. So I am going to pause the video and I will be back in 5 minutes. Okay, so now let's look at an application problem that uses quadratic equations. Now, the interesting thing about example 18, and I'm just going to say to you that you're probably not going to see something like this on a test, but I do want to share this with you because it's really interesting. So we want to factor that expression, right? But in order to do this, what we're going to want to do is find the solutions to the equation first, and then use the solutions to find the factors. So it's this idea of, you know, where was it? Let me write this. It's the idea of knowing what the solutions are, writing them in factored form. And we say, okay, this is the factored form of our polynomial. We're looking for these. We're looking for these factors. So what will help in this case, instead of trying to factor something as chaotic as this, we can just find the solutions first. And we could do that using the quadratic formula. So let's write down that A is equal to 54, B is 93, and C is 40. It's huge, right? So this is why it's going to be helpful to solve first and then write out the factored form based on the solutions. So we have x is equal to negative b, so negative 93, plus or minus the square root of gross b squared, which is 93 squared, minus 4 times a. I know you're probably thinking like, ugh, this is huge. It's true, it is, but we're going to punch in everything in the calculator anyways. Over 2 times a, so it's 2 times 54. All right, let's check this out. So negative 93 plus or minus. In our calculators, we're going to take 93 squared minus 4 times 54 times 40. Oh, and what do you know? All of that is 9. Thank freaking God. Otherwise, that was going to be the worst. All over 2 times 54, which is 108. Okay, cool. So let's finish this off. We know that the square root of 9 is 3. This is a perfect square. So this becomes x is equal to negative 93 plus or minus 3 all over 108. So I want to write out my 2 solutions. So the first solution is negative 93 plus 3 over 108. And if it's okay with you, I'm just going to do the math. So negative 93 plus 3 is negative 90. So that leaves us with negative 90 over 108. With negative 90 over 108, we definitely want to simplify this to lowest terms. If I take the 90 ABC 108, I find that this is the same as negative 5 over 6. So I'm going to write out my first solution is negative 5 over 6, because we're going to end up using this solution just like we did with our previous problem. I also have negative 93 minus 3 over 108. So negative 93 minus 3 is negative 96 over 108. So if I punch this in, 96 ABC 108, that's going to give me negative 8/9. So there's my second solution. X is equal to negative 8/9. We learned in order to figure out what those factors were that we wanted to multiply each equation by the LCD. Hey, Jeff. So we're going to multiply both
Hey,
sides
Professor.
by, we're going to multiply by 6. And the second one, we're going to multiply by 9. So that leaves us with 6x is equal to, notice the 6's cancel, -5. And then I want to bring that 5 over. So 6x plus 5 is equal to 0. With the second equation, we have 9x is equal to, notice the 9's will cancel, so it's equal to -8. And then, of course, we want to bring that -8 over by adding it. So we have 9x plus 8 is equal to 0. And just like that, I have found the factored form of our original equation. So we were able to use a quadratic formula to find both of our solutions, write the solutions out, and then work backwards to find the factored form. So 6x plus 5 times 9x plus 8 gives us 54x squared plus 93x plus 40. Trying to factor that using AC grouping might have been the worst experience we've had in a while. So this is nice. Use a quadratic formula, find the solutions, and then, of course, work backwards. Very nice. So I'm going to note here that this is the factored form of our polynomial. Kind of cool, right? Something to think about. The things that are available to you given specific techniques, like in this case, the quadratic formula. Awesome. We're now ready for a projectile motion equation. So think about, all those times you see the problems where they're like, somebody's on the top of a building and they kick a ball, right? And then they're on top of the building, they kick a ball and then after a certain amount of time, it follows this trajectory and then boom, it hits the ground. And they usually say, how long did it take, before the ball hit the ground? Or how high above the ground was it after 5 seconds, right? Or something like that. So all of these projectile motion equations deal with that kind of, parabolic shape, that parabola shape, which is exactly what we're doing, the x squared, right? Degree of 2. So let's take a look at how we would break this down in general form. So the height h of an object t seconds after it is projected upwards is modeled by this specific equation, where the g here is acceleration due to gravity. This v sub 0, right, like Mortal Kombat, v sub 0, it's the initial velocity of the object. And then h sub 0 is the initial height of the object. So you'll essentially be given either the equation or you'll be given the information that will help you to write the equation itself. So let's check this out. Suppose a ball was hit upward on the moon from an initial height of 2.65 feet. This is something to think about. We were just told the initial height is 2.65 feet. So immediately I know that this is h sub 0, my initial height, with an initial velocity of 132.5 feet per second. My initial velocity is v sub 0. The gravitational acceleration on the moon, gravity on the moon, is about -5.3 feet per second squared. Obviously, it's stronger on Earth. So that's our gravity. So what we want to do is we want to essentially rewrite the equation. So we want to write down what this actually means. So what we'll do is we'll fill in our values into our equation. So it's h is equal to 1/2. G is -5.3. Then we have t squared. That's not going to go anywhere. We're not replacing t with anything. Plus our velocity, which is 132.5. And then we have t. Notice we're just filling in the equation. And then plus our initial height, which is 2.65 feet. So essentially, there's our equation. What we may want to do, though, is we'll probably just want to multiply these so that we simplify it. So I'm just going to rewrite the equation. So h is equal to, if you take 1/2 and you multiply it by -5.3, that's going to give you negative 2.65. So negative 2.65 t squared plus 132.5 t plus 2.65. How long after the baseball was hit would it reach a height of 132.5 feet? How long? When you see this how long piece, I want you to think, I don't know the time. But what I do know is the height. I know the height is 132.5 feet. So what you're going to want to do in this case is we're going to want to make a substitution. Every single time you're given information, substitute it into the equation and then move forward from there. So let's check this out. So we have 132.5 is equal to, let's write the rest of the equation. I'm just writing everything we have down. And now I want to solve this. We know that if we wanted to solve this, we've got to set this equal to 0. So I'm going to subtract 132.5 from both sides so that I can set this equal to 0. Let's bring this over, make a line as straight as possible. 0 is equal to negative 2.65 t squared plus 132.5 t. And then we have 2.65 minus 132.5, and that's going to give us negative 129.85. Okay, hopefully so far, so good. We want to solve this. Well, we can use the quadratic formula. I wouldn't use anything else. That would just be really, really disgusting. So let's use a quadratic formula where A is negative 2.65, B is 132.5, and C is negative 129.85. Okay, so X is equal. In this case, X is T. So instead of writing X is equal to, I'm going to write T is equal to. That's what's replacing X in this case. This is my input. So T is equal to, so we have negative B, 132.5, plus or minus the square root of B squared minus 4 times A times C, all over 2A. I don't want you to panic about how crazy this looks. When you see that our original problem has a whole bunch of decimals, what that implies is that your answer can also be in decimal form. So what I would recommend to you is to literally plug this entire thing in all at once. So let me show you. The square root of, we have 132.5 squared minus 4 times negative 2.65 times negative 129.85, and then we close it and we get 127.2. That's everything here. So that's the square root of the entire expression here. That's going to be incredibly helpful if you just do this in one fell swoop. So now what we have is T is equal to negative 132.5 plus or minus 127.2 all over 2 times a negative 2.65. That's going to give me negative 5.3. We are looking for two solutions here. We're going to start by taking negative 132.5, adding 127.2. Oops, I typed this in wrong. Negative 132.5 plus 127.2. And then we're going to divide that by negative 5.3. When I do that math, I get that T is equal to 1. Let's find the other solution. Negative 132.5 minus 127.2. And now let's divide that by negative 5.3. And that's going to give you 49. So in this case, notice that we actually have two solutions. So what this is saying is that it's going to reach a height of 132.5 at t is 1 second after it's hit or 49 seconds after it's hit. If that is confusing to you, I think a visual is going to be incredibly helpful. So I'm going to write the original equation, negative 2.65 t squared plus 132.5 t plus 2.65. And I'm just going to graph this so that you can see what this equation looks like. Let me share with you my Wolfram alpha, because you're probably thinking, how is that possible? Notice that my increments here are in terms of thousands. So somewhere around here, really low, is where the height is 132.5. Notice that that crosses at two places. So it's crossing when time is 1, so t is 1 second, right? Because what comes up must come down. And then again, when t is 49 seconds. So it's somewhere around here, okay? That's why this makes sense. It's in two locations. Okay. So how long after the baseball is hit would it reach a height of 132.5? It would be after 1 second and then again after 49 seconds. So after 1 second and again after 49 seconds. Okay, that's essentially what we're looking at, after 1 second and then again after 49 seconds. For part B, it says how long after the baseball was hit would it hit the ground? So again, how long? Well, that means I don't know t. But if it hits the ground, doesn't that mean that the height is 0 if it hits the ground? So I'm going to go ahead and replace height with 0. And we'll write out the entire equation, negative 2.65 t squared plus 132.5 t plus 2.65. We're going to use the quadratic formula again to solve this. I love using the quadratic formula for something with decimals because all we have to do is punch it in and solve. So in this case, we have t is equal to negative b, so negative 132.5 plus or minus the square root of, and this time obviously our values are going to be a little bit different underneath because for our previous problem, our C was negative 129.85, but this time our C is 2.65. So we're not going to copy down exactly what we had before. We want to be careful with that. So B squared minus 4 times A times C all over 2A. Perfect. So again, I'm going to punch in the entire expression here, including the square root. So the square root of 132.5 squared minus 4 times negative 2.65 times positive 2.65 gives us a very long decimal. So we've got negative 132.5 plus or minus. When I punched all of that in, I got 132.6059, etc. If I were you, I would probably round to this place. Typically, I do 4 decimals, but 5 will make this into a 10, which will make this into a 6. So why not just round to this place instead? Just so that we're as accurate as possible. 132.60596 all over negative 5.3, because that's 2 times a negative 2.65. All right, let's find our two solutions. So t is equal to, so we've got negative 132.5 plus 132.60596 divided by negative 5.3. And that gives me a negative solution. So negative 0.01999. Okay. Obviously, this doesn't make any sense. We want to know how long after the baseball was hit would it hit the ground. Negative time. This doesn't make any sense. So let's do the second one. Negative 132.5 minus 132.60596. And then, of course, divide that by negative 5.3. When we do this math and we round to the nearest tenths place, we get 50.0. Notice what I have in my calculator, 50.019. So let's round to the nearest tenths place, and it's 50.0 or 0.2. If you want to round to the hundreds, we can do that as well. So it would hit the ground in 50.02 seconds. That's how long it would take for the ball to hit the ground. Last part, what would the height of the baseball be after 25 seconds? So we want to know the height. We don't know. What would be the height? I don't know. But we know the time is 25 seconds. This is great because that implies I can replace my variable t with 25 and then simply plug this into my calculator. We don't know the height. We still have the equation, which is negative 2.65 t squared. T is 25, so we're going to replace t with that 25, plus 132.5 t, but t is 25 seconds. So again, we're just subbing out the t with 25, and then plus 2.65. Remember, you're always using the original equation. So let's punch this into our calculators. Negative 2.65 times 25 squared, plus 132.5 times 25, plus 2.65. Solving gives us 1,658.9. So consider that height is in terms of feet. So after 25 seconds, the ball reaches a height of 1,658.9 feet. And there's your answer. Okay. As always, if there are any questions, please don't hesitate to ask me. I'm hoping that this was pretty straightforward. There's a lot, I know there's a lot going on in these problems, but it's all manageable. You just have to take your time as you move through these. The biggest piece of advice I can give you is identify what you're missing and what you're actually given. Typically in these kinds of equations, you only have two unknowns, right? I have an h, which is height, and t, which is time in seconds. Cool. If I give you one, you can solve for the other. That's going to be incredibly helpful to think about, okay? If you have one, solve for the other. Beautiful, beautiful, beautiful. Let's move into other types of applications in problem solving. So for example 20, we're told that a repair shop projects that its annual profit, P of T, in thousands of dollars over the first 7 years in business can be approximated by that function. So P of T is equal to 0.4 t squared plus 4.4 t minus 8, where t is measured in years. This is very important, okay? So the annual profit is P. P is profit, T is years. Estimate the profit or loss, right? Depends if it's positive or negative, of the repair shop after the first year. So immediately when you see that, I want you to think about the information that you're given. If you're told after the first year, T is measured in years, so that must mean that T is equal to 1. That's what that is telling you. So we're going to use the function. So we have P of T, but we know that T is 1. So we want to find P of 1. which means everywhere we see a t, we replace it with a 1. 0.4 times 1 squared plus 4.4 times 1, right, because t is 1, minus 8. Punch this into your calculators. This piece I really, really like because a lot of it is just write out the equation and then plug this into your calculator. When we do the math, we find this is equal to negative 3.2. What this means is that at the end of the first year, a loss of 3.2. Now keep in mind the profit or loss is in thousands of dollars. So a loss of $3.2 thousand is projected. At the end of the first year, a loss of $3.2 thousand is projected. Let's do it again and see what's happening over time. So for part B, estimate the profit or loss of the repair shop after the 6th year. So that means that T is equal to 6. So let's see if they can expect a profit after being in business for a while. So we have P of 6 is equal to 0.4 times 6 squared plus 4.4 times 6 minus 8. So again, all we're doing is plugging in. Everywhere we had a T, we replace it with a 6. Aha. And now we notice that P of 6 is equal to 32.8. That is fantastic news. Essentially what this is saying is that after year 1, they can expect a loss, right? Because they're a new business. They probably have a lot of expenses initially. And then what's happening over time is they're building their base, right? They're working with more and more people and they're able to actually profit. So notice here that the projected profit is $32.8 thousand. Fantastic. So at the end of the 6th year, a profit of $32.8 thousand is projected. That's fantastic. They're going in the right direction. What part C is asking us is to estimate the time, right? To figure out how much time is needed for the repair shop to break even. When you see that phrase break even, I want you to think of the fact that the profit when you break even is 0. Right? You're not losing, you're not gaining, you broke even. So your profit is $0. So having said that, what that means is in our equation, that profit, that P of T part here gets replaced with 0. So that's exactly what we're going to do. We're going to rewrite it as 0 is equal to 0.4 T squared plus 4.4 T minus 8. Our objective is to solve this. Because we want to solve, obviously we're going to use the quadratic formula. Our X variable is actually T, that's our input. So we're going to say T is equal to, and now let's use the quadratic formula. So we have negative B, B is 4.4, negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. Cool. Let's do the math. Same thing. I'm going to plug in the square root of 4.4 squared minus 4 times 0.4 times negative 8. And then I get T is equal to negative 4.4 plus or minus. I get a really crazy long decimal, not a big deal. I'm going to round to, we're going to do 5 places. So that's going to be 5.67098. 5.67098 all over, and then 2 times 0.4, well, that's just going to be 0.8. So let's find both solutions here. Negative 4.4 plus 5.67098. Divide that by 0.8, and we get t is equal to 1. We'll round to the nearest tenths, 1.6. Let's punch in the other one, negative 4.4 minus 5.67098, and then divide that by 0.8. And you also get t is equal to negative 12.6. Clearly, we're going to throw away this negative time because it's not negative 12.6 years is when they break even. That doesn't even make sense. So we can say the repair shop will break even after 1.6 years. So they'll break even between years 1 and 2, which is pretty cool. So after year 2, it's looking like they're just going to start to make more and more money. All right. Very, very nice. I'm telling you, these are fantastic for that reason. We have 2 unknowns. If I give you one, you find the other. No big deal. No big deal at all. Especially since you're being provided with the actual formula. So essentially all you have to do is plug and chug. Right? Okay, perfect. All right, let's take a look at this next example. A runner jogs 6 miles and then turns around and jogs back to the starting point. Okay, cool. Now keep in mind, if the runner jogs 6 miles and turns around and goes back, it's a 6-mile return, right? 6 miles to the destination and 6 miles back. The first part of the jog is mostly uphill. So the speed average is 2 miles per hour less than her returning speed, right? Because then she's moving downhill. Unless you're me and then your knees are terrible. And when you go downhill, your knees hurt so bad that it's like you need to take a break every 10 seconds. Yeah, I'm old. If the total time spent jogging is 1 3/4 hours, which we can write as 1.75 hours, find the speed going and speed returning. Okay, something to keep in mind. I'm going to really quickly write that as 1.75 hours. That's the total time, right? That's how long it took. We are going to use our distance formula. We're going to keep in mind that we know that distance is equal to rate times time. But we also know that because we're talking about total time, that we're actually going to want to solve for time. So distance over rate is time. We're right back to what we did a long time ago. Let's draw up our chart. We have rate, time, distance. Keep in mind what's happening in this scenario. We're talking about her going uphill and downhill. So uphill and downhill. So I don't mind writing it this way, uphill and downhill. You are told that she jogs 6 miles uphill, right? And then she turns around and she jogs 6 miles back. So that part should be very straightforward. Keep in mind the distance is in terms of miles. It's a nice thing to kind of jot down. The first part, because it's mostly uphill, her speed, or this runner, I'm automatically assuming the gender, which I shouldn't. So the speed is 2 miles per hour less than her returning speed. Oh, there it is. Okay. So it's 2 miles per hour less than her returning speed. What that means is that her speed downhill, we don't know what it is. But what we do know is that uphill, she averaged 2 miles per hour less. So we're going to write that as R minus 2. Be careful not to write it as 2 minus R. That doesn't make any sense. Like, what if her speed downhill is like 9 miles an hour? You wouldn't say her speed uphill is 2 minus 9, because then that's a -7. Who's running -7 miles per hour? That's weird. So we want to be careful. Keep in mind also that less than implies the reverse, right? You're essentially writing it in the opposite order. So it's her rate minus 2 miles per hour. Good. I'm going to write above rate that we have miles per hour and that our time is hours. Recall that time is always distance over rate. So for the uphill time, we can write 6 over r minus 2. And then for her time downhill, it's 6 over r. Okay, we have all the information except for one piece. We are told the total time spent jogging for the whole thing is 1.75 hours. So what that means is that her time uphill plus her time downhill should equal 1.75 hours. The total time is 1.75. Cool. We're right back to where we were before. Time uphill is 6 over r minus 2 plus 6 over r. If we were in session together, I know right away a couple students who would specifically say, let's multiply by the LCD, which is fantastic because that's exactly what we want to do. Jose, she's definitely one of them. We're going to multiply every term by the LCD, which is r times r minus 2. R times r minus 2. We're going to multiply here, here, and here. Cool. The r minus 2's cancel. 6 times r is 6r. Plus, the r's are going to cancel, so we have 6 times r minus 2. And then we have 1.75 r times r minus 2. And I'm just going to write that out. Okay. Logically, our next step is to distribute to drop parentheses. We don't want to leave parentheses anywhere. So we want to open all of this up. So we have 6r plus 6r minus 12 is equal to, now remember, you're distributing 1.75r, not just r. So 1.75r times r is 1.75r squared. And then we have 1.75 times negative 2r, which is going to give me negative 3.5r. Awesome. I think at this point, Oliver would say set this equal to 0. So we're going to combine like terms here. This is 12r minus 12 is equal to 1.75r squared minus 3.5r, and we will bring these over. We want to set this equal to 0, so then we can use the quadratic equation to help us solve. So I'm going to subtract 12r, and I'm going to add 12. Setting this equal to 0 leaves us with 1.75r squared. Combine these two, negative 15.5r, and then plus 12. Okay, very cool. Let's use the quadratic formula. A is 1.75, B is negative 15.5, and C is 12. Notice X is the same as R in this case. So we write R equals, it's not X equals, it's not T equals. It's based on whatever variable you have here. So we're solving for R using the quadratic equation. So R is equal to negative B. B just happens to be negative. It's not a big deal. So negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. Anytime I see problems like this, I'm like, yes, I don't really have to do too much except for, plug it into my calculator and see what value I get. So the square root of negative 15.5, let's try this, the square root of negative 15.5 squared minus 4 times 1.75 times 12. And it's the square root of that entire expression. When you plug in this entire expression, you'll get 12.5. 2 times 1.75 is 3.5. So let's find both answers for R and see what happens. So the first one is 15.5 plus 12.5, then divided by 3.5. So I get r is equal to 8. Let's find the second one. 15.5 minus 12.5, and then of course divide that by 3.5. And then I get 0.857. So we essentially have two solutions here, but I want you to think about what this actually means. So if, for instance, we say that, okay, well, the rate's positive, doesn't that make sense? Check this out. If the rate is 0.857, and I plug that back in here for my rate uphill, you're gonna have a negative rate. So that right there tells us, no, we're gonna throw that one away because that one's not gonna work. It's not a valid rate because she can't move down, she can't move uphill at a negative speed. So I'm gonna cancel this one out. So what I notice here is that if r is 8, let's take a look. If r is 8, then my speed downhill is 8 miles per hour, and the speed uphill is 8 minus 2, which is 6 miles per hour. So let's write our solution. She jogs 8 miles per hour downhill and 6 miles per hour uphill. And that is your solution. What I would suggest to you all is doing the next problem on your own. So with 21, we took up the entire page. Again, it's not a big deal. We have our chart, we fill in our information just like we did before. We always write out the equation in words because that's going to be helpful. Plug in the values. If you have to multiply by the LCD, do that. You multiply by the LCD, distribute to drop parentheses, set it equal to 0, use a quadratic equation, and solve. Don't overthink it. I want you to do the same thing for problem number 2. So this one you're going to do on your own. Okay, so I'm going to put a little star here, here, here. I would like you to do example 22 on your own. A Cessna plane flew 80 miles with a 30-mile-per-hour wind and then made the return trip flying against the wind. The total flying time out and back took 1.3 hours. Find the speed of the plane in still air. Okay, I want you to attempt this using your distance chart. When we return on Monday, we are going to start by solving for a variable in a formula, which you actually could probably do this right now. It's really, you know, I have 5 minutes. I'm going to do this page so that way when we come back, we get to finally graph. That's what I really want to get to. Okay, so we have about 5 minutes left of this session. We will pick up on Monday here, graphing quadratic functions. So make sure that you are working on all of this material over the weekend and working through your Unit 4 homework in Lumen. I will tell you that I plan on assigning the rest of the homework due the last day of class. We only have 1 week left and our last day is next Thursday. So everything moving forward from here on out, all of that homework will be due Thursday. Please don't wait. If you wait, that's a disaster. Okay, that's going to be a disaster waiting to happen. You have a comprehension check for chapter 3 and 4. It's already there. So as soon as we finish chapter 4, you'll be able to actually accomplish a comprehension check, and you will have a test associated with that. I know that the last test is going to be so close to the final, but it's going to be great preparation for that final. The final exam will cover everything that we've done this semester. It's not going to be a huge test. I'm only going to pick certain questions that I think are very pertinent to your learning for Math 104. Okay, that's neither here nor there. We'll talk about that next week, but make sure you're prepared by doing all of your work up to this point, all of Unit 3 and most of Unit 4 by early next week. That's the plan. Okay, really hustle. We only have 1 week left. Okay, let's do this one page and then we'll call it a day. In order to solve for the indicated variable, we do the same thing we always have done. Isolate that variable by using the opposite operations, right? So, okay, we want to solve for b. I have b in my second term, which means I've got to move a squared. So let's bring that over. If I bring a squared over, I now have b squared is equal to c squared minus a squared. Well, if I want to solve for b, then I must take the square root of both sides, right? We use the square root property. Just remember something very specific. If you use the square root property, that leaves you with a positive or negative solution. So it's positive or negative c squared minus a squared. We can't actually go forward from there because you can't take the square root of each piece individually. This is c squared minus a squared. This is an expression. So you're not able to just take the square root of each piece. It doesn't work that way. We're done. That's it. That's it. Take a look at part B. I want to solve for capital R, but that's being trapped by 4 pi. Instead of distributing 4 pi, because remember, I want to focus on how do I use the opposite operation. So instead of distributing, I'm actually just going to divide by 4 pi. Since it's 4 pi times everything else. The 4 pi's cancel, and just like that, I open up r squared minus r squared, capital minus lowercase. Cool. I need to solve for r, capital R, so I'm going to bring over tiny r. I have a over 4 pi plus r squared. Please don't combine these. It's not true. That r squared is not over 4 pi, so it doesn't make sense to combine those. Last step, take the square root of both sides. Don't forget, it's a positive and negative result. So our answer is plus or minus square root of a over 4 pi plus r squared is equal to r, and you're done. Cool, right? I told you it'd be pretty straightforward and not too bad at all, actually. Let's look at part C. We have a is equal to that fraction. This is v sub 2 squared minus v sub 1 squared all over 2d. Again, we need to multiply both sides by the LCD so that we can eliminate fractions. So this gives me 2dA, which you could write 2AD, doesn't matter, is equal to, notice those will cancel, v sub 2 squared minus v sub 1 squared. Don't freak out about the whole v sub 2 and v sub 1. It's just notation. Keep in mind, we're trying to solve for v sub 1. And I'm actually going to suggest something to you that you may find a little bit odd. I'm actually going to bring the v sub 1 squared over and then move the 2dA over to the other side. I'm going to swap places. So I'm going to bring v sub 1 over this way. So that leaves me with v sub 1 squared plus 2dA is equal to v sub 2 squared. And then I'm going to bring the 2dA over to the right. So that way my v sub 1 squared is actually positive. So that goes away. So v sub 1 squared is equal to v sub 2 squared minus 2dA. Cool. Last step. Take the square root of both sides. Squared and a square cancel each other out. V sub 1. That's going to be equal to positive or negative. Whoops, not x. My brain. It's fried. It's been a long week. V sub 2 squared minus 2dA. You're done. All right. Last one, we want to solve for C. Notice we have 3 times the square root of c squared minus v squared. I'm actually going to divide both sides by 3. That says v prime, like prime, P-R-I-M-E, v prime. So v prime over 3 is equal to the square root of c squared minus v squared. Well, I want to get rid of the square root so that I can open up everything that's underneath. What's the opposite of square root? Square. So I'm going to square both sides. This is going to give me now v prime squared so that it's not confusing. I'm going to write as v prime squared. 3 squared is 9. The square root and the square cancel each other out. Now everything's revealed. You have c squared minus v squared. You want to solve for c. So the first thing you're going to do is bring over the v squared. We have v prime squared over 9 plus v squared is equal to c squared. And last step, take the square root of both sides. I know there's a lot going on, but I hope that you found this to be pretty straightforward. You just use the opposite operation every time. And we're done. Awesome. As promised, we will pick up on Monday with graphing quadratic equations. We will finish our notes on Monday. That is a promise, which means we may move into Unit 5 on Monday as well. So make sure you print those out. The other thing to consider is Unit 5 is actually really small. I'm going to be like literally throwing out a bunch of pages from Unit 5 because a lot of it is 098 material. It's just a recap of what we did last semester. My advice to you is before class on Monday, if you need a refresher, go to my 098 playlist and check out solving systems of equations, and maybe even check out motion problems in 2 variables. So take a look at those, maybe even mixture problems in 2 variables. Check those out so that way you are adequately prepared to move into 104 content. That, again, that's only if you're a little bit shaky with how to solve systems of equations. So like, for instance, do you remember how to use elimination or substitution? If you do, you're golden. If not, check out those videos, get a quick refresher, because moving into Unit 5, I want to start with the 104 material. I don't want to start with 098 material. It doesn't make sense to do that. Unit 5 is super small. You'll notice that the homework assignments for Unit 5, there are only 2. Okay, it's a very, very quick, it's very short, and we end with trigonometry, which is actually a lot of fun. Make sure you have your calculators handy, especially for that section, because you're not going to be able to use your calculator, your cell phone calculators. All right, everyone, have a wonderful weekend. Good luck with everything that you're doing. Please don't hesitate to reach out to either Jeff or myself. We would be happy to assist you with whatever questions you may have. Okay, and of course, the Math Learning Center. Cool. Bye.
See ya.
See ya.